We are ready to start the session, and it's my absolute pleasure to introduce you James Madden, that will talk about recent work on conjunctive joint similarities.
Thank you. So we have till 10:55 or?
Yeah, exactly. 25 and
My alarm is going to go up.
yeah.
That'll stop me.
Okay.
If nothing else then. This is work that the three of us did over the past several years. We were lucky enough at LSU to have David Gato as a visitor starting in the summer of 2019. And then even luckier when COVID came in and forced her to stay. What we did was started a seminar and searched for a topic that we had a common interest in. And we sifted through a number of different things, Z ideals and F rings and so on, until we finally hit on conjunctive joint semilattices as a simple topic that kind of encompassed at a very abstract and remote, at the most possible abstract and remotely abstract level, the themes that were common to what we were looking at. So I'll mention in a later slide exactly something about how that fits into other things that we were interested in. Here's a summary, and I mean, there's just 9 slides in the talk, but they tend to be crowded. I'll talk about some background, give the definition of conjunctivity, then and its connection to some topics in mathematics that are surely of interest, probably. I'll talk about the representation theorem that we have for these objects, and some properties of that representation theorem, including its punctoriality, which is kind of sketchy. So that's something that we could, we worked hard and for a long time to try to make the symbolism work properly. And we haven't actually applied anything here, but it appears to work in a nice way. And then one of the big topics related not just to conjunctive joint semilattices, but to joint semilattices generally, is the topic of distributivity. So joint semilattice is distributive. And this is a topic that's described in detail in Retzler's book on lattice theory. Joint semilattice is distributive if every binary cover or every finite cover of any element has an exact refinement. That is, if A and B together soup above C, then there's something less than A and something less than B that together soup to exactly C. And that's an amazingly powerful condition. And it has as a consequence, that's well known, that every ideal that is maximal missing a filter is prime. But one thing that we discovered was that the converse is true. So if in any joint semilattice, if every ideal that is maximal missing an element is prime, then the joint semilattice is distributive. And I thought this is basic. Well, the analogous statement for distributive lattices is trivial by the representation theorem. But distributive joint semilattices don't have the properties that varieties have, and so the simple argument that works for lattices doesn't work there. And I'm going to end the talk with a challenge, a very simple question that we've been working on for months and that we can't answer, and maybe some perspective that maybe a fresh perspective that somebody has on this would be useful. Okay, so a joint semilattice, of course, is a set equipped with a commutative associative idempotent operation. We can order it, order any joint semilattice, we can order such a thing by declaring that A is less than B if the soup of A and B is equal to B. that's in the ordering defined in that fashion. A sub B is the least upper bound of A and B. Our joint semilattice doesn't need to have a top element, but we always demand it has a bottom element. I was thinking about that. We did a lot of work trying to prove theorems about joint semilattices that don't have a bottom element. And that turned out to be cause a lot of problems. Trying to work with those things is like looking in the eyes of somebody who's not wearing a shirt in a bar somewhere. You don't want to tangle with that. All right. Of course, any post set that has the least upper bound of any finite subset is the joint semilattice. A lot of the literature deals with meet semilattices. You can simply dual to joint semilattices, and everything that we prove for one of these things has a statement for the other. An ideal is a non-empty down set that's closed under soup. An element of a joint, an element of the set of, right, of course, the two element totally ordered set is a joint semilattice. JSL is a set of all joint semilattice maps from L to 2. We call such thing a character. If phi is a character, then the inverse image of 0 is an ideal. And if I is an ideal, then the mapping, then the characteristic function of the complement is a character. And the first place I think that these were talked about in detail was in a paper by Pepper that appeared in the 60s. She was interested in understanding the lattice of congruences of the joint semilattice and used this fact extensively. Much deeper is Pontryagin duality, which, as a matter of fact, I wasn't aware of until quite recently. And the Pontryagin duality for joint semilattices could give a very interesting new perspective on a lot of the results that we've worked on. The two element set is all, in addition to being a joint semilattice, it's also a topological, a discrete topological space, and a topological joint semilattice. It plays the role of a schizophrenic object. Right? John is both, I think. Right? A lot of natural dualities are representable, and the codomain of the Tom function that gives the duality is called the schizophrenic object. So 2 in this case plays the role of the schizophrenic object. The set of all joint semilattice mappings from L to 2, L being a joint semilattice, is a closed subset of the stone space because any mapping from L to 2 that fails to be a joint semilattice map fails because of an example that gives you a neighborhood of that failure that doesn't intersect the Ham set. And conversely, if we let A hat be the mapping from be the evaluation map, then it's a topological joint semilattice mapping as described there. And we get an isomorphism. And I don't want to talk about this in detail, but it's there and it should be investigated. It's very interesting.
So it's between joint semilattices and topological joint semilattices?
That's right, yeah. The not all topological, zero-dimensional, compact topological. Yeah. Okay, so a joint semilattice is said to be conjunctive if it has a top element, and for any elements A and B, if B is not less than A, then there is a C such that the sup of A and C is not equal to 1, and the sup of B and C is equal to 1. This is a condition like this first appeared in Wallman's paper on the Wallman compactification in 1938, except the dual condition, and he called it disjunctivity. I think the name conjunctivity came from Simmons, who wrote a paper on this topic in the 1970s and investigated this as a separation property in topological spaces. We started, if A sup C is equal to 1, then we call C an upper complement of A. And the conjunctivity condition is saying that if two elements have the same upper complements, then they are the same element. Right. An ideal of L is said to be maximal if it doesn't contain A and any properly larger. It's said to be amaximal if it doesn't contain A and any properly larger ideal does contain it. If I is an ideal of L that doesn't contain A, then of course by Zorn's lemma, there's an amaximal ideal containing I. If we say maximal without qualification, then we're talking about then, and we have a then we need one maximum. And here's a fact: if L is conjunctive, if and only if for any two elements A and B, if B is not less than A, then there's a one maximal ideal of L that contains A and doesn't contain B. So there's enough maximal ideals to distinguish between the zero sets, to distinguish between elements. We can run through the proof quickly. If B is not less than A, then we can pick a C so that, right, we're going forward from the conjunctivity hypothesis to the existence of maximal ideals. If B is not less than A, then we can pick a C so that A sub C is less than 1 and B sub C is equal to 1. The principal ideal generated by A sub C doesn't contain B, so it's contained in a B maximal ideal. But that ideal contains A sub C. Any larger ideal contains B and therefore contains 1. So it's maximal. And conversely, we just use the facts about what it means to, if we have a maximal ideal that contains A but not B, then any larger ideal contains B. So there's something in the I. And it's the same kind of argument. Okay. This condition is reminiscent, and Simmons pointed this out. It's reminiscent of the Jacobson condition on commutative rings. Jacobson, a ring is called Jacobson if every prime ideal and hence every radical ideal is an intersection of maximal ideals. In the Sachs project, they christened a topological space to be Jacobson if every closed set is the closure of the set of its closed points. And it so happens that the following are equivalent. R is a Jacobson ring. Spec R is a Jacobson space. But we can rephrase this. Maybe it takes a little bit of work to do this, but it's not complicated. But the frame of all radical ideals of R, which is the topology of the spectrum, of course, or is order isomorphic to the topology of the spectrum, is conjunctive. So the conjunctivity condition is very closely related to the condition of being the Jacobson ring, and being the Jacobson ring is important in algebraic geometry. Conjunctive frames, right, frames and semilattice with some additional information. So a conjunctive frame, they're called subfit. As a matter of fact, the definition of subfit frame is exactly the same as the definition of conjunctive semilattice. It has subfitness has a lot of interesting characterizations and plays an important role in point three topology. That's one of the is an important separation property. A frame is subfit if every proper frame congruence, if in every proper frame congruence, the congruence class of 1 is not singleton. The same characterization also applies to conjunctive frame semilattices. Here's a problem that I thought of while we were writing this up. We could call a ring finitely Jacobson if the radical ideal of every finitely generated ideal, if the radical of every finitely generated ideal is an intersection of maximal ideals. What can we say about such rings? Right, this is the rise of the natural, because the spectrum, right, the topology of the spectrum of a ring is a coherent frame. It's the frame of ideals of the lattice of finitely generated radical ideals. Now, a joint semi-lattice or a lattice can be conjunctive without its frame of ideals being conjunctive. So what does this condition mean? I have no idea. It's an open problem and an interesting one. The representation theorem is like this. Let L be a joint semi-lattice with one. Max L denotes the set of one maximal ideals of L in the topology generated by the set, the co-zero sets. Co-zero set is, or the co-zero set is the inverse image of one under a character. And this would be a co-zero set would be the inverse image in the set of maximal ideals of one under a character. All right. So the T1 condition is obvious because maximal ideals are incomparable. Incomparability of ideals translates into the T1 condition. For compactness, and this was a surprise to me, right? And there's the analogy doesn't go any deeper. The spectrum of a lattice, in a spectrum of a lattice, the compact opens correspond to the elements of the lattice. In this case, it's only the top that's compact. The other elements, don't give rise to compact sets. So, but the proof is quite easy. If B is a set of elements of L, and the co-zero sets of the elements of B cover max L, then that means that no maximal ideal contains B. That's a simple translation of the condition. That in turn implies that the ideal generated by B contains one. Because if it didn't, then there'd be a maximal ideal that contains it. So that means that there's a finite subset of B whose suit is one. That means that this cover has a finite subcover. Well, we were dealing with the subbase. Right? So every cover by elements, by subbasic elements, has a finite subcover. L in the subbase theorem gives us that set is compact. We don't need any conjunctivity hypothesis to create this representation, if you want to call it that. But the conjunctivity is equivalent to this representation being injected. The mapping from A to cos A is a mapping from L to the set of all two-valued functions on max L. That mapping is injective if and only if L is conjunctive. As a matter of fact, the kernel of that mapping is described as follows: co-zero set of A is equal to co-zero set of B, if and only if A and B have the same upper complements. We can move that. The representation is idempotent. That is, if I represent a joint semi-lattice, right, and then take the representation of the representation, I get the same space-time. So that's all that's saying. So that means that if you want to think about conjunctive joint semi-lattices, what you're thinking about are subbases for compact T1 spaces. Here's a little example. This is called the diamond. It's the counter example. It's the, it's one of the obstructions to a lattice being distributive. It is as a Hasse diagram, it's a top and a bottom and three incomparable elements in between. There are three maximal ideals, but none of them are prime. Okay, an ideal. I've got time is getting short. An ideal of a joint semi-lattice is prime if its complement is a filter. That's the definition of primeness in this context. And there's a nice proposition here that says that I won't do the proof. this is an argument that appears in Gretz's book in this section on representations of distributed joint semilattices. But the conclusion is that all the maximal ideals of a conjunctive joint semilattice are prime if and only if the cozero sets form a basis, not merely a subbasis. That is, if and only if every open set in the representation space is a union of cozero sets. You don't have to take intersections. And this is the first hint that primeness is a very interesting and powerful feature. The functoriality, I don't know if I want to talk about. This is this ugly. Let's see here. See, there's the all right. The hat here is the representation. So if we have a morphism of joint semilattices, then we define phi hat, a mapping between the representation spaces. So hat is a covariant function. So we define it this way. We need a hypothesis on the morphisms. That is that we need psi inverse of every maximal ideal to be an intersection of maximal ideals. Right? It's an obvious condition that is required in order to be able to represent morphisms. But under those hypotheses, then A hat souped with phi hat, that is the representation of A following the representation of phi is the representation of phi of A. We get that equation, or we need a little, right, this is a multifunction, not just a function. So we need to define what we mean by a composition of a multifunction. So we use a supremum to do that. So we get something that looks like the functoriality that we have in other more usual representations. And, but we don't have continuity here. But we got a multifunction, so what is continuity? All right. We have the analogous condition, lower semi-continuity, under the assumption that all the maximal ideals are prime. So that's the functoriality of the representation. Let's now talk about distributivity. We can define several forms of distributivity at an element. So if the distributivity that I described at the beginning of the lecture is true at an element, if every cover review has an exact, if every finite cover review has an exact subcover, then that's I say that U has property D. If we call this a conductor, right? If the set of elements, if for all A, the set of elements that soup A above U is a filter, and this was a form of distributivity that was defined in an article by Varla in the 70s. And then I say that U has property V, and finally I'll say that U has property P if every U maximal ideal is prime. And then it can be proved, and this is it took some work to go in the difficult direction, but it can be proved that V of U is equivalent to P of U. And it can also be proved that V of U implies D of U, and that D for everything for U and everything less than U implies phi of U. So that means that distributivity in the for the entire lattice implies the primeness is equivalent to the primeness condition. The forward implication is well known and is part of the is described in Gretz's book as He doesn't even prove it explicitly. It's a generalization of the subject matter described earlier. Although I think he's a little bit optimistic about his readers' abilities. He was optimistic about my ability. I didn't think about that for a long time. For lattices, as I said previously, the opposite implication is trivial, but it's new and evident, seemingly non-trivial for transient lattices. Two more minutes, if I may get your indulgence. For conjunctive joint semilattices, the following are equivalent. V of 1, not V of the whole thing, but V of 1 is of course equivalent to all the maximal ideals being prime. But we can have, right, we can satisfy V of 1 without having distributivity in the whole joint semilattice. That's an interesting case. Now here's the challenge, and this turns out to be a very difficult problem. It looks very basic, but this is the question. Suppose that I've got a joint semilattice that has two elements, S and T. Suppose that the downset of S is a joint semilattice of the top element, so is the downset of T, right? If both of those are conjunctive, does it follow that the downset of S sub T is conjunctive? And the answer is no, not necessarily. There's an easy example, but it's not distributed. So in the case of finite distributive joint semilattices, this is true. And we argue as follows. It wasn't trivial, but first of all, a finite conjunctive joint semilattice is actually a Boolean algebra. Second, if theta is a non-trivial joint semilattice congruence on a Boolean algebra, in which the class of every atom is a singleton, then L mod theta is not distributive. So those are facts I can find. Yeah. But so with the finiteness hypothesis, we get the result that we hope for. The question is, can we weaken or even omit the finiteness hypothesis? And this is an instance of this is suppose I take the push out of a couple of conjunctive joint semilattices over a common ideal. Is that conjunction? So we've been agonizing about this for months. We have no idea maybe they'll put us out of our misery. Oh, maybe somebody will probably put us out of our misery. Okay, thank you.
Thank you. I'm going to allow like a short question. And do we have something from the present audience? No, there are comments on recordings. So, do we have comments from the online audience? You can unmute yourself and just ask.
I have a simple question, because I've never seen this definition or defined like this. Ideal is prime if the complement is a filter.
Yeah.
So then for prime filters, would it be that if its complement is an ideal?
Yeah.
Okay.
Yeah.
That's what we've seen it with the just, if A and B is in there. Then
Yeah, it's right, because I think that this idea of considering distributive joint semilattices came from people in the 60s, I think, that were interested in understanding. There's a conjecture about the representability of algebraic frames as congruence lattices. So an algebraic frame is the frame of ideals of a distributed joint semilattice. This is So this definition, right, arose in that context. And then the definition of a prime ideal in this context was introduced. I think the definition goes to this paper of Ritzer and Schmidt in the 1960s.
Okay, so let's thank our speaker again, so we can.